In this example, we want to use nodal analysis to calculate the current IA flowing through the 8 ohm resistor. This circuit is important because students will learn how to handle voltage sources in the nodal procedure. In particular, the concept of supernode is demonstrated here. First, we identify all the nodes. Be careful at not finding any more nodes than there actually exist in the circuit. Also, students tend to miss the node between the 8 ohm resistor and the 4-volt source. Remember that any two circuit elements are typically separated by a node. We have here 5 nodes in the circuit, thus 4 node voltages are going to come from that. Secondly, we select a reference node. Now, in terms of the validity of the solution, the choice of reference node is arbitrary. But when voltage sources are present, particularly independent voltage sources, the selection of the reference node requires special attention. For example, this circuit has 5 nodes, thus 4 unknown known voltage. I typically select the negative terminal of an independent voltage source as the reference node. That way, we know the node value at the positive terminal. Here, 4 volt where the red arrow points. We have in effect reduced the number of unknowns from 4 to 3. This is what I call a smart selection of the reference node. Next, we label all other nodes beside the reference node. Note I put 4 volt on the bottom node. V1, V2, and V3 are my unknown node voltages for this problem. The next step is to put current arrows and labels on all resistors. Now, folks, the 8 ohms already has a current IA. Let's not add another current. We do not put current labels and arrows on sources at all. Now, remember that the direction of the current is totally up to you at this point. There is no right or wrong direction for these currents. You pretty much can pick whichever you want, and it's perfectly valid at this point. Now, form a supernode around each voltage sources. Basically, a supernode is a large blob that surrounds the voltage source and its 2 nodes. Only voltage sources, folks, and nodes should ever be found in a supernode. Now, if 2 supernodes share a common node, then these 2 supernodes must be combined into a large supernode. Now, you could also have 3 supernodes sharing a common node, and they also must be combined. Here, this is not the case, so we have 2 separate supernodes. What's coming ahead? Now we know we have 3 unknowns, and obviously we need 3 equations. These equations will come from, 1, we're going to be writing the dependent source output in terms of the node voltage. Realize that we already did that for the 4 volt source by saying that the bottom node is equal to 4 volt. But for the dependent source, we are writing V1, where the plus sign is, minus V3, where the minus sign is equal to 4IA, the output of that dependent source. That, in effect, is our first equation for the 3 unknowns V1, V2, and V3. Next, we do a Kirchhoff current law equation at node V2. Node V2 is a regular node. What I call regular node is a node that is neither the reference node nor does it belong to a supernode. It's a regular node. And we write KCL about that node V2. Sum of the current leaving the node is equal to 0. Thus, I3 plus 6 amp plus IA is equal to 0. You will note that I do my KCL equations in terms of currents. This is to avoid combining both KCL and Ohm's law, which often leads to sign errors on the part of students. In many textbooks, you see that. You see essentially the authors doing both KCL and Ohm's law at once. It's perfectly acceptable, but it's unlikely you're going to get it right over and over again. So I'm going to strongly suggest anytime you write a KCL equation, do it in terms of current, and then we'll do Ohm's law and then put them in and collect terms. The last equation comes from the KCL about the supernode V1, V3. We only write KCL equations about supernodes that do not contain the reference node. In essence, the one on top, which it's green here, is the only supernode that does not contain the reference node. The bottom supernode contains the reference node, so we don't write KCL about it. When we write KCL about a supernode, folks, we basically consider the supernode as a big dot. We look at this blob and look at current coming in equal current coming out, or the sum of the current into that blob equal to 0. Here we have I3 coming in, 6F coming in, I2 coming in, and I1 leaving. At this point, we've essentially finished our three equations, three unknown. We just need to manipulate them or use Ohm's law in the next part to convert current to voltages. Having written the three equations for the unknown, we use Ohm's law to convert or write the currents I1, I2, I3, and IA in terms of the node voltages. Every time we write Ohm's law equations, the passive sign convention should be in our mind. It should be recalled. For example, we chose the direction of I2 arbitrarily because when we started the problem, we didn't know where current flows. We have no idea what the values of current or voltages are. So we picked those directions of the currents totally arbitrarily, and that's fine. So we selected I2 going from bottom to top. But once we do that, that implies that the plus sign is at the bottom node where the 4 volt is, and the minus sign is where V1 is. And by doing that, or by thinking that way, we're saying I2 is equal to 4 volt, where the plus sign is, minus V1 divided by 2 ohms. The selection or the positioning of the plus and minus sign for the voltage on the current or about the current follows the passive sign convention, which states that the current must enter at the positive terminal. Using Ohm's law equations into the KCL and the source equations, then we put them in, put them into the same denominator, and collect terms for V1, V2, and V3, and we end up with three equations, three unknown to solve. Now, previously I talked about using Cramer's rule and at least learning to use Cramer's rule. It's still something that I think you all should learn, to use Cramer's rule to solve system from order 2 to order probably 5, as probably our concern here will be at most a system of 5 equations, 5 unknown, to solve this kind of problem, because in the future you may face a situation where you have equations that do not have numbers. But having solved these equations, we'll calculate the node voltages, V1, V2, and V3. And that's pretty much, you're almost done with the full solution to this problem. And then we can calculate IA, which is simply V2 over 8. And the problem is solved. Now, in conclusion, this example is probably as general as it gets at that level. In other words, if folks can solve a problem that looks like this, what I mean by that is that contain voltage sources, contain dependent sources, and have generally 3 or more nodes, then I think you're in good shape. That is the target that you should do at this point.